Okay, so previously we've talked about confidence intervals as one way to make determinations about having collected data and about population parameters. Now we're going to talk about hypothesis tests. And I know you've used the term hypothesis in science. And just as a review, a hypothesis is just an assumption about a population parameter. Of course, the assumption may or may not be true. It's just that what we currently believe to be true, just from based on other things we've observed. So what is hypothesis testing? It's a formal procedure used to retain or reject a statistical hypothesis. Now, it's kind of interesting that I said retain. We actually never go around and prove it. We never prove a hypothesis. Now, we may reject it, but we never ever prove it. So either we reject it or we retain it. Now, I want you to consider this is a lot like a jury trial. So in a jury trial, we assume the defendant is innocent. So our null hypothesis or our initial claim is that they're innocent. And we retain that hypothesis unless the facts make that unlikely beyond a reasonable doubt. Then and only then we reject it and we declare the person guilty. On the other hand, if we don't find enough evidence to say that they're guilty, we don't say they're innocent, we just say that they are not guilty. So the same logic can be used for hypothesis tests. We begin by assuming that the hypothesis is true. Next, we consider whether the data are gathered, the data are consistent with the hypothesis. And basically, we sit there and we gather evidence to try to prove that the hypothesis is false. Now, in a court of law, there's some evidence that helps the defendant and there's some evidence that hurts the defendant. And the same is true with hypothesis testing and statistics. We've gathered some data. The question is whether or not there's enough to reject the initial claim. All right? Once again, we never prove the null. We didn't gather evidence to prove it. We only gathered evidence to disprove it. All right? So how do we know when we've done that? Well, we collect a thing called, we create a p-value. And in that case, we're able to quantify our level of doubt. Because whenever we do a hypothesis test, whenever we go to a court of law, there is a possibility that the defendant is not guilty, and we say that they are guilty. Why? Because we don't know all the facts. Generally, we weren't there. And even eyewitnesses' accounts have been shown to be flawed. So there's always some level of doubt. Usually we just sit there and you wait till it gets small enough. Well, how do we quantify it? Well, in statistics, that's the p-value. Now, the fact of the matter is you've already been calculating p-values. We just didn't tell you that's what it is. And basically a p-value is a conditional probability and gives the likelihood that we'd get a test statistic as extreme or more extreme given that the null hypothesis is true. And that probably didn't make a lot of sense. But for the time being, let's go with that, and we'll talk about it in just a moment, a little more in detail. So here's what our statement would be about p-value. Given that the null is true, there's a 1% chance we'd calculate a test statistics as extreme or more extreme in favor of the alternative. So consider this. You have a friend who claims that he scores 25 points in every single basketball game, or on average scores 25 points a game in basketball. And you kind of doubt that. So you take a random sample of games and you go, okay, my average ended up being 22 points. And he did score more than 25 points once, etc. And so it's like, well, maybe that's true, maybe it's not. Well, when you calculated the probability, once you actually calculated the probability, you said, well, there's a 25% chance that he would only score 22 points if his claim of 25 points or more is accurate. And then you have to make a decision. Wow, am I going to believe them and sit there and go, you know what, I can't disprove his 25-point claim, or am I going to say, you know what, he's lying, he doesn't score 25 points or more a game? And really, we have to determine, we set a determination as to where we're going to reject the null. That rejection level is known as the alpha. All right, and we've already calculated alpha when we did confidence intervals, and that was the area in the tail. So typically, we say 5%. You know, well, he only could make it 22% of the time. I mean, we got a p-value of 22%. Well, p-value of 22%, that doesn't sound that bad. That sounds like we probably should be rejecting, but consider this. You only want to reject the null if there's a reasonable level of doubt. In other words, it needs to be rare. And I'd like you to consider the number of pickups in the Reagan parking lot. Well, that's probably about 1 out of every 5 vehicles, or even if it's 1 out of every 10. If it's 1 out of every 5, that would be 20%. And you go, well, that's really not that rare. I mean, it's not the common, but it's not really rare. And even if you said 1 out of 10, well, that would be 10%. And you're like, gosh, I still don't consider seeing a pickup in the Reagan parking lot that rare. So we pick a value that we consider really rare, and typically we compare to a value of 0.05 or 0.01. But most of the time, and if they don't tell us, we'll use 0.05. You're like, well, why 0.05? And it's simply this: we're happy with a 5% error rate. And you're like, what? No one's happy with errors. I'm like, well, we kind of are. Consider this: if you had a 20-question multiple choice test and you missed one question, you'd make a 95. And while that's not perfect, and while you want 100, you're never really going to be upset about a 95. And so we're generally, and that's like, well, I got 95% right, so I knew 95% of the material correctly. It also meant that you knew 5% incorrectly. And it's like, so we're kind of okay. We're hardwired in a way we've grown up to accept a 5% error rate when we're talking about things. So typically, if we have a p-value less than 0.05, we will reject. So if it turns out that our p-value for the guy playing basketball was 0.22, we'd probably go, you know what? We didn't see it. We didn't prove that he makes that many points, but his claim might be true, and we can't reject it out of hand because it could happen 22% of the time by random chance alone. And continuing on with the trial, as we've said, it's much like a court trial, and we assume that they are innocent. In other words, we assume the status quo or the claim to be correct, and then we present evidence, which in our case is the data. And if the probability of that data is extremely small, less than 5%, we reject the null and we go and we take the alternative being that they're guilty. And once again, you're like, well, does it always have to be 5% or 1%? And no, it doesn't. And depending on the problem, we'll give you different percents. But if we don't give you a percent, use 5% or 0.05 if we don't give it to you. So what do you do with a quote unquote innocent defendant? Remember, we didn't prove them. They're innocent. If the evidence is not strong enough to reject the presumption of innocence, the jury returns the verdict of not guilty. They don't say they're innocent. Well, in statistics, we don't say that we prove the null. We don't say that we accept the null. We don't say that the null is true. We just have this really kind of awkward term that says we fail to reject the null. So in other words, if there's not enough evidence to reject it, we say we fail to reject it. So our two choices in statistics are going to be reject or fail to reject. Now, this will have reject has a small p-value, fail to reject will have a larger p-value. Reject is going to be a small p-value, generally less than 5%. Fail to reject will have a larger p-value, typically greater than 5%. All right. We also make this sometimes we say the null hypothesis has been retained. When I say I retained it, didn't mean that I agree with it, didn't mean it was true, didn't mean any of those things. It just, we didn't get rejected. We kept it, even though we may or may not have wanted to. We didn't find enough evidence to flat out reject it. Below are the 4 basic parts of to a hypothesis test. I highly recommend you read through them, but I'm going to break that down further when I go through the recipe card. So, our vocabulary. We know that a hypothesis is an assumption about the characteristics. In this case, we are testing the population means. We know that hypothesis testing is a method of determining the validity of the hypothesis. Is the claim likely to be true? Once again, we never prove that the claim is true or false. We either reject or fail to reject. As a matter of fact, some of you go, well, I want to be 100%, make sure that I'm 100% true. We can't be. And the reason we're not able to is because we're taking a sample. And with the sample, we don't have every single piece of data evidence. We have some, we may even have a lot. Since we don't have every single data piece, we're taking an estimate. And as such, we cannot be 100% true. You're like, well, what if I went out and collected every single data piece? If you did that, you collected a census, and we don't need statistics, and we don't need hypothesis testing. So if you do a census, you're not going to need hypothesis testing, and you're not going to need confidence intervals. And really, you don't need statistics, because you will know the true population parameter. You'll know the true population mean. All right, so the nice thing about the null hypothesis, we write HO and we say that's the null, okay? It will always be an equal sign. And if we're testing means, it'll be mean equals some number, all right? Mean equals some number. I'd use 0.81 here, but it could be something else. But the null will always be equal. The alternative, which is probably the most challenging part of all of hypothesis, has 3 different choices. It has a not equal, a greater than, or a less than. And you're going to need to read the question carefully to determine which type it is, all right? And then, so not equal, the claim the population mean is different than the claim, all right? So the key word here is different. So look for different, and by the way, we probably should scratch these out and use the word mean instead of proportion, but we'll use proportions later. This is greater than, so we're looking for is larger, is increased, is more, words like that. And this, of course, is the less than. And anyway, regardless how it's expressed, the HO will always have an equal. So the null always will have an equal. HA can be one of these 3 symbols, and they'll be determined based on the question. One other thing to talk about, a not equal claim is a 2-tailed test in which alpha is divided into both tails. And if you remember, when you did a 90% confidence interval, we had 0.90 here, and then we had a lower bound and an upper bound. And if I go 1 minus 0.90, I get 0.10, and that gives me my alpha level of 0.10. Well, alpha is the area in the tails. So my area in the tails are 0.10. But you say, Mr. Spencer, there's half in this tail, which is 0.05, and half in this tail is 0.05. And I go, that's correct. There's half in each tail, but together the area of the tails summed to 0.10. So my alpha level is 0.10. It's split between 2 tails. When I do an upper tail test, it's going to look something like this. Using 90%, although it's not going to be a confidence level, I'm going to have 0.90 here and an alpha level of 0.10. And this would be using a greater than or upper tail test. And a lower tail test, this is going to be 0.10 and the 0.90 up here. Please note, this is my rejection zone, and this is my rejection zone. Out here is the rejection zones. So what does that mean? Well, if we end up with a value that's too far this way or too far this way, we reject. That value is the p-value. If the p-value is too far to the left or too far to the right, we reject. On this one, we only reject if it's too far to the right. And on this one, we only reject if it's too far to the left. So one tail, lower tail, reject when it's go left. One tail, upper tail, reject when it goes right. The two-tail test, it can be left or right as long as we're too far away from the center. All right. I would read all this information as it's very, very important, but this part is 3-star, I cannot stress enough. We reject if the p-value is less than alpha, and that's a period. Forever and ever, always, amen. We fail to reject if the p-value is greater than alpha. So if our p-value is greater than alpha, we fail to reject. If it's less than alpha, we reject. Okay, so the recipe for success. It's going to be very similar to the ones that we did for confidence intervals, but it does have some differences. The very first thing is we're going to need to write our hypothesis, and it's going to be the null mu equals some number, some value. We don't know what it is, but it's going to be some number. The alternative, we're going to write mu, and we're going to write that same number, but we're going to have to choose an inequality, less, not equal to, or different. The keyword usually is different, something that's less or something that's greater. Then we're going to define our parameter in context, and that's going to be our let mu equal the true population mean statement, just like we did before. Our conditions, because this is regular, because of the stat list class, we're just going to assume. We're going to write our equation, and this equation should look very familiar to you because we've used this before when we're talking about central limit theorem. The x bar represents the sample mean. The mu is the population mean. This is the standard deviation of the population, and n is the sample size. And of course, z just tells you how many standard deviations you are from the mean. Next, we'll draw the graph and shade. We'll enter the data if they've given us data. They don't always give us data. Sometimes we just have statistics. We're going to list and label all of the input values. So you're going to make a list of all these values, whether you inputted data and you got that from the one var stats, or whether you they gave it to you in the problem. We're going to plug all these values into this equation. And then we're going to calculate by using a number one z-test enter. All right, so this is the key phrase. Z-test enters happens to be a number one, and we'll enter the data. Finally, we'll state our decision. We'll go the p-value is, and they'll calculate it on step 9. It'll calculate it, and we'll write the p-value is this. We're going to compare it to alpha. If alpha is less than if the p-value is less than alpha, we reject the null. If the p-value is greater than alpha, we fail to reject. If no alpha is given, use 0.05. And then we have our statement. Our p-value is, and that came from number 10. It also was calculated in number 9. We reject the null. That's if we're rejecting. If we chose the rejection one, we're going to choose this value. So if we choose this one, we're going here to reject. There's sufficient evidence that alpha equal whatever we chose to suggest the true population mean for. This is where we're going to restate our defining the parameter let mu equal the true population mean, and then restate the alternative hypothesis. If we fail to reject, it's going to be the same thing, except our p-value is number 10. But instead of reject, we're going to fail to reject. So we have a difference here, because this is the rejection one, this is the fail to reject. And instead of being there is sufficient, there is not sufficient. So please note that if we're failing to reject, it's a not. And that's the only differences between the two, the way those two things are stated. I will tell you once again, just like on the confidence intervals, the recipe card is a step-by-step process. You must follow it. And if you do, you'll make an A. And I can assure you of that. All right, thank you for watching this video. The next video, we will actually do a scenario.